Welcome to Orbit Observer. Settle in. Let your shoulders come down from wherever they've been hiding all day. There is nothing you need to do for the next little while except breathe and drift and let a quiet voice carry you a very long way from here. You don't have to follow every word. You don't have to remember any of it. If you fall asleep before I've finished, that's not a failure. That's the whole idea. This is a place to let go. Tonight I want to take you somewhere cold and dark and impossibly far away and tell you about two of the smallest, gentlest things in the whole solar system. Two little moons, two quiet, potato-shaped worlds circling a blue planet at the outer edge of everything we know. And I want to tell you about the strangest, softest thing they do, a thing they have done, without a single mistake, for longer than there have been people on the Earth to wonder about it. Here is where we're going. Out past the Sun, past the warm inner worlds, past Mars, past the great striped giant Jupiter, past Saturn and its rings, past pale Uranus, tipped over on its side, all the way to the last of the great planets, Neptune, a deep, deep blue. A world of methane and wind, drifting in a place so remote that the sun out there looks like nothing more than a very bright star. And swimming close around that blue planet, skimming just above its cloud tops, are two tiny moons named Naiad and Thalassa. And this is the thing about them. This is the thing I want you to carry down into sleep with you tonight. Naiad and Thalassa ride two paths around Neptune that are almost exactly the same. Their orbits, the invisible tracks they follow through the dark, are separated by only about 1,850 kilometers. That's it. Barely 1,850 kilometers between one moon's road and the other's. Let me put that in something you can hold. 1,850 kilometers is a smaller distance than the width of many countries. It's a drive you could make in a couple of long days. On the enormous scale of a planet and its moons, it is nothing at all. It is a hair's breadth. It is 2 lanes of the same highway, 2 swimmers in neighbouring lanes of the same pool, 2 worlds sharing almost the very same circle, one just barely inside the other. And yet, in all the time they have been circling, in all the countless laps, the endless quiet revolutions around that blue giant, Naiad and Thalassa have never touched. Not once. Not a graze, not a bump, not a brush. They come around and around and around, closer together than seems possible. And every single time they pass, they miss. Cleanly, peacefully, perfectly, sit with that for a moment. 2 objects, sharing nearly the same path, so close their tracks are only that thin sliver apart, and they never collide. It sounds like it shouldn't be possible. It sounds like something that should have gone wrong a long, long time ago. 2 things that close, moving that fast, forever, surely, eventually, on some unlucky pass, they'd meet. Surely the timing would slip just once. But it never does. And tonight, slowly, gently, I'm going to tell you exactly why. Because the reason they never touch is one of the loveliest, most reassuring things I know about the sky. It isn't luck. It isn't distance. It's a kind of choreography, a dance so precise and so patient that the danger, the real and constant danger of 2 worlds skimming past each other, is simply, quietly, resolved every time. Forever, as far as anyone will ever see. Here is how the dance looks, and I want you to picture it, because it's the image I'd like you to fall asleep inside of. Naiad is the inner one, riding just slightly closer to Neptune, moving just slightly faster. Thalassa is a touch farther out, moving a touch slower, And because Naiad is faster, it slowly catches up to Thalassa from behind, lap after lap, gaining on it the way a slightly quicker runner gains on the one ahead over many circuits of a track. Naiad gains, and eventually it comes up right alongside its neighbour, ready to overtake. And this is the moment. This is the moment when, if the two moons were riding the very same flat circle, they'd be in terrible trouble. Two worlds coming up beside each other on the same ring, at the same height, in the same plane, that's exactly the recipe for a collision. But they are not on the same flat circle. And here's the secret. Naiad's path is tilted. Just a little. Just enough. Where Thalassa's orbit lies almost perfectly flat, like a plate held level, Naiad's orbit is tipped at a gentle angle, leaning slightly up on one side of Neptune and slightly down on the other. And because of that little tilt, when Naiad comes up to overtake its neighbour, it isn't beside Thalassa at the same height at all, it's above it, or below it, riding over the top or slipping underneath. So picture it now. Naiad comes gaining up from behind, and as it draws level with Thalassa, it rises up and over the top of its neighbour, passing safely above, like one bird lifting gently over another, clear, untouched, and then it moves on, pulling ahead, going around again, all the way around Neptune, and it comes back for the next pass. And this time, because of the tilt, because of the patient geometry of it all, this time it sinks. Down and under, passing safely below Thalassa, gliding beneath it. Clear again. Untouched again. Up and over. Down and under. Over the top, then beneath the bottom. That's the dance. From Thalassa's point of view, if Thalassa could watch, its little neighbour would seem to weave, rising over its head, then dipping under its feet, then over again, then under again, threading past like a needle, stitching over and under a single thread of cloth. Never level with it, never in the same place at the same time. Always just high or just low. A perpetual gentle near miss that resolves every single time into a clean and quiet pass. Over the top, under the bottom. Over, under, that's the rhythm of it, and it's a rhythm the two moons have kept, without error, for an unimaginably long time. Now if you're lying there in the dark and some part of your mind is still braced, still waiting, the way it does at night, for something to go wrong, I want you to hear this. That thing you're bracing for, in this story, never comes. That's the whole point of where we're going tonight. Here is a system that looks like it's on the edge of disaster. Two worlds a hair apart, forever, and the disaster simply never arrives. The near miss always resolves. The danger is real, and the safety is built right into the machinery of it. You can watch two moons come that close that many times and let go of watching, because the outcome is always the same. They miss. They're fine. They go on. So let that be the shape of the night. A danger named and then dissolved. Named and dissolved. Over and over, as softly as breathing. Before I take you deeper, let me ask you something, and you can answer it in the morning or in your head right now as you drift. Where in the world are you listening from tonight? What city? What quiet room? What corner of the earth is holding you while I tell you about these two little moons at the far edge of the sun's reach? I always love to know. Down in the comments, whenever you feel like it, no rush, it'll keep tell me where you are and I'll read it. I read all of them. And if you're new here, if you've only just found this quiet little place, you're very welcome to stay. Subscribe if you'd like the next slow story to find its way to you when you need it. Then let it go and come back to the dark with me, because I want you to understand how far away all of this is happening. how remote, how untouched, how deeply, restfully distant. Neptune orbits the Sun at a distance of about 4.5 billion kilometers. 4.5 billion. That's a number so large it stops meaning anything, so let me trade it for one that's a little easier to hold. Astronomers use a measuring stick called an astronomical unit, and it's simply the distance from the Earth to the Sun, the whole span of our own orbit, the entire distance across the sky that our year is made of. 1 astronomical unit. And Neptune sits about 30 of those out, 30 times farther from the Sun than we are. If the Earth's whole journey around the Sun were a single step, Neptune would be 30 steps away, out in the cold beyond the streetlight. And this far out, the Sun is barely a sun at all. Out at Neptune, sunlight is only about 1/900th as bright as the sunlight we know. 1/900th. Think of a bright afternoon here, the kind that makes you squint, the kind that pours through a window and warms the whole room. Now dim it, and keep dimming it, 900 times over, until what's left is a soft, silvery dusk that never fully lifts. That's noon on Neptune. Noon out there is a deep and gentle twilight, a permanent blue evening. The Sun in that sky is not the great golden disk we grew up under. It's a single, very bright point of light, no wider than a distant star, casting long soft shadows that barely change all day. That's the light Naiad and Thalassa dance in. Not brightness, not glare. A cold, dim, endless twilight, 4.5 billion kilometers from the fire that made everything. They weave their over and underweave in near total darkness, in a hush so deep and so far away that for most of human history we had no idea they were even there. And they move fast. That's the strange, beautiful contradiction of them. Everything about this scene sounds still, the distance, the dimness, the dark, but the moons themselves are racing. Naiad, the inner one, circles all the way around Neptune in only about 7 hours. 7 hours, a whole orbit, a complete lap around an entire giant planet, done in less time than a night's sleep. Thalassa, a little farther out, takes a little longer. About 7.5 hours to come all the way around. Both of them whip around Neptune in less time than a single working day. Less time than you'll spend asleep tonight. Let that settle. While you lie here and drift off, while you sleep and turn and dream and wake in the morning, out at the cold edge of the solar system, Naiad will have gone all the way around Neptune again, and again, and again, a full lap every 7 hours, another every 7, another and another, tireless, silent, weaving over and under its neighbour the whole time. By the time you open your eyes, these two little moons will have completed the dance dozens of times over, without a single misstep while you rested. There's something in that I find deeply calming. The universe keeps its rhythms whether we watch or not. The dance holds while you sleep. Now, how do we even know about them? How did anyone ever find two dark little moons, only tens of kilometers across, tucked in close against a planet 4.5 billion kilometers away, lost in that permanent twilight? For almost all of human history, we didn't. We couldn't. They were far too small, far too dim, far too close to Neptune's glare to be seen from here at all. They were secrets the dark kept very well. And then, once, only once, in all of history, we went out to look. Directly, in person, with a machine we built and sent. There is a spacecraft called Voyager 2. And Voyager 2 is the only spacecraft that has ever visited Neptune. The only one, ever, in all the years of the space age, with all the probes we've flung across the solar system. Exactly one machine has ever travelled out to that blue world and looked at it up close. Just one. Voyager 2, and no one since. It reached Neptune in the summer of 1989. It made its closest approach on the 25th of August, 1989, sweeping in over the planet's north pole, passing only about 4,950 kilometers above the top of Neptune's clouds. Skimming just above that deep blue atmosphere, moving fast, with only a brief window to see everything it could see before the planet's gravity slung it onward and away into the dark. A single flyby. A few precious hours of close looking after a journey that had already lasted more than a decade. And in that brief pass, as Voyager 2 studied Neptune and its winds and its rings and its great moon, it also caught sight of small, faint specks of light close in against the planet, little moons no one had ever seen before. Two of those specks were the moons in our story tonight. When Voyager 2 first found them, they didn't have names yet. They had the plain provisional labels that new discoveries get, the kind of temporary tags you scribble on something before you've decided what to truly call it. The one we now call Thalassa was labelled S1989N5. The one we now call Naiad was labelled S1989N6. Just codes. A designation for a satellite discovered in 1989 at Neptune, the 5th and the 6th, found in that encounter. Two dim little points of light, catalogued in passing by a spacecraft racing by, given numbers before they were given names. And I want you to feel the loneliness and the wonder of that for a moment, because it's part of what makes them so precious. Everything we learned about these two moons in that first encounter, we learned from a single machine, passing once, more than 30 years ago. We have never gone back. No other spacecraft has ever made the trip. Voyager 2's brief look in August of 1989 is, to this day, the only time a human-made thing has ever been out there in person to see Naiad and Thalassa with its own eyes. One visit. One glimpse. And then the long silence of the dark again. There's a rarity in that I find almost tender. We know these worlds, and yet we've barely met them. We caught them once, in passing, like two faces glimpsed from a train window, and we've been piecing together their story ever since, from that one fleeting encounter and from patient looking across a great distance. They are among the least visited places we have names for. And still, from that single pass and the careful work that followed, we learned that they were there, and roughly how big, and where they rode, two small dark moons, circling in close, keeping their impossible distance from each other in the twilight. Later, of course, they got their proper names, and the names are lovely, and they fit. Neptune is named for the god of the sea, so his moons are named for the spirits of water. Naiad, a naiad in the old Greek stories, is a nymph of fresh water, a spirit of springs and streams and quiet pools. And Thalassa is older and larger in the myths. Thalassa is the sea itself, the primordial goddess who is the personified ocean, the deep from which so much else was born. A freshwater nymph and the ancient sea circling the sea god out in the dark. Even the names are gentle. Even the names sound like water moving softly in the night. But hold on to that first image of them as Voyager saw them, just faint specks, catalogued as N5 and N6, brief glints against the blue. Because here's what's remarkable, and here's one of the threads I'll pull on for you as the night goes deeper. Voyager 2 saw the moons. It found them. It counted them, it measured roughly where they were. But it did not, in that single passing glance, understand what they were doing. It did not see the dance, the over and under weave, the tilted threading, the perfect avoidance. None of that was clear from one flyby. Voyager caught the dancers in a single frozen moment, but it could not watch them move for long enough to see the rhythm they were keeping. That secret stayed hidden for another 30 years. And when it finally came out, when someone finally worked out how these two little moons truly move around each other, the answer was so elegant, so precise, so quietly reassuring, that I still find it hard to believe it took us that long to see it. But that part of the story is for a little later. Let it wait. There's no hurry here. For now, just stay with the picture. Stay with the two little moons in the twilight. 4.5 billion kilometers away, 30 steps out past the sun, in a light so dim it's barely light at all. Two dark, potato-shaped worlds, small enough that you could very nearly drive across either one in an afternoon if there were any roads. Racing around their blue planet, one lap every 7 hours, faster than you'll sleep tonight, and yet, for all that speed, moving with the patience of something that has all the time in the world. Naiad on the inside, a touch faster, slowly gaining. Thalassa on the outside, a touch slower, holding its steady line. The gap between their two roads only that thin sliver, 1,850 kilometers, closer than the width of many countries. And every time Naiad catches up, every time the two of them draw level and the moment of danger arrives, the tilt saves them. Naiad rises over the top or sinks beneath the bottom. Up and over, down and under, a near miss resolved into a clean pass, and then around again, and the same safe outcome, every single time. Why don't they smash together? That's the question at the heart of tonight. Two worlds that close, that fast, forever, why haven't they collided? It's the kind of question that could keep you up if you let it. It has the shape of a worry, the shape of a thing that surely, eventually, must go wrong. But I promise you, this is a worry that answers itself. This is a danger with a solution built right into it, a solution so reliable that the two moons have never once needed luck. And over the course of this long, slow night, I'm going to hand you that solution, piece by gentle piece, until the worry has nowhere left to stand. For now, all you need is the picture and the promise. Two small moons, a tilted track, a near miss every few hours that always resolves in peace. Let me slow it down even further, because I don't want to rush past the sheer strangeness of how close they really are. 1,850 kilometers between their paths. On the map of a planet, that is nothing. Neptune itself is nearly 50,000 kilometers across. You could line up more than 25 of those little gaps just across the face of the planet the moons are circling. The gap between their two roads is a fine line, a pencil stroke, against the great blue bulk of the world they orbit. If you were somehow standing on Thalassa, looking up as Naiad came around to overtake, your neighbour would not be a distant dot in a far-off sky. It would loom. It would come up close and near and real, a whole ragged little world sliding past. Close enough to feel like it might reach out and touch you, and then it would rise or fall, lift over your head or slip beneath your feet, and go on by and shrink again into the dark. And you would be untouched. And you would wait, and it would come around again, and the same thing would happen from the other side. Above you this time. Or below, imagine standing there through pass after pass, the near approach, the bracing, and then, every time the gentle lift or the gentle dip and the safe going by. After enough passes, I think you would stop bracing. I think you would learn, in your body, that the miss always comes, that the tilt always saves you, that there is nothing to fear in your neighbour's approach, because the shape of the whole arrangement guarantees the pass will be clean. You would learn to watch it come, and simply trust the geometry and let it go by, and rest. That's what I'd like for you tonight. To learn from these two little moons the same soft lesson, that not every close thing is a collision, that danger and safety can live in the very same motion, that a system can hold itself together gently and reliably through pass after pass after pass, without anyone standing guard, without anything going wrong. The old original tracks are still turning out there right now as you lie here. In the deep blue twilight, 4.5 billion kilometers away, Naiad is gaining on Thalassa again, coming up from behind again, closing the small distance again. And in a little while it will draw level, and the tilt will lift it up and over, and it will pass above its neighbour, clean and quiet, and go on around. And a few hours after that it will come back and slip below, over and under, above and beneath. While the far-off sun hangs like a bright star in a sky that never quite brightens, and the great blue planet turns beneath them both, and nothing at all, goes wrong. We didn't always know this. For almost all of time, no one on Earth had any idea these two small moons existed, let alone that they were keeping this patient, tilted rhythm out in the dark. And then one machine, one time, in the late summer of 1989, went out and caught the first faint glimpse of them, labelled them N5 and N6, and moved on into the deeper dark, leaving us with just enough to know they were there and to begin the long, slow work of understanding what they were doing. That work would take another 30 years. And what it uncovered, the exact, extraordinary reason these two worlds never touch, is where this story is heading. But we have all night, so let's not hurry toward the answer. Let's stay a while longer here at the edge of everything, in the quiet and the cold and the almost dark, watching two small moons come close and part, and never, ever collide. There is a rhythm to it that I think your breathing is already starting to match. The slow approach, the gentle lift, the safe passing by, the long, unhurried loop back around. Naiad gaining on Thalassa, over the hours, the way sleep gains on you now, patiently, from behind, closer and closer, until it simply, softly overtakes. Let it. There's nothing out there to guard against tonight. The moons have this handled. They've had it handled for longer than anyone can count, and they'll have it handled long after this night is over. Two little worlds, a hair apart, weaving past each other in the dark, over the top and under the bottom, and around again, keeping perfect, peaceful distance, in a twilight 4.5 billion kilometers from home. Stay with me. We're only just beginning to understand how they do it. And every piece of the answer, I promise you, is another reason to let go. So let us start with the simplest thing, the thing that makes all the rest of it feel almost impossible to believe. Naiad, the innermost of the two, rides its path around Neptune at a distance of roughly 48,200 kilometers from the planet's center. Thalassa, just one step outward, rides its own path at roughly 50,000 kilometers from that same center. The gap between them, the space that separates one orbital track from the other, is on the order of about 1,850 kilometers. Not 800,000 kilometers. Not 8,000. 1,850. A little less than the length of the eastern seaboard of the United States, roughly less than the straight-line distance between London and Istanbul. Less than the width of the Mediterranean Sea at its broadest stretch. In a solar system where planets are separated by hundreds of millions of kilometers, and where even neighboring moons around giant planets often ride orbits tens of thousands of kilometers apart from one another, 1,850 kilometers is nothing. It is a whisper. It is the kind of gap that when you first encounter it written down in a table of orbital parameters makes you stop and read the number again. Because surely it has been printed wrong, surely a zero has been dropped somewhere, surely two real moons sharing a single planet's gravity cannot be riding paths that close and simply not have run into each other by now. And yet, Naiad is there at 48,200 kilometers, circling Neptune in about 7 hours, give or take. Thalassa is there at 50,000 kilometers, circling Neptune in about 7.5 hours. And the count of their encounters without collision is not a dozen, not 1,000, not 1,000,000. The count is a number so large that it has no comfortable home in ordinary language, a number that belongs to the deep and patient arithmetic of solar system time, which measures not in years, but in eons. They have been doing this, as far as anyone can determine, since long before the first fish breathed air on the shore of any ocean on Earth. They will, as far as anyone can determine, still be doing it long after the last one. There is something about that span of time, held against the smallness of the gap, that the mind keeps coming back to. 1,850 kilometers. 7 hours per lap, countless encounters, 0 collisions. Something is making this work. Something is keeping the gap safe, despite the fact that nothing about its size suggests it should be safe. And the first piece of that something, the first mechanism, the first quiet engineering trick that nature has built into this system has to do with the shape of Naiad's path and the shape of Thalassa's path, and specifically with one crucial difference between them. Thalassa's orbit, as best as the measurements can determine, lies almost perfectly in the plane of Neptune's equator. If you imagined Neptune's spinning middle as a great flat ring extended out into space, a paper-thin disk reaching out to 50,000 kilometers, Thalassa would be riding, very nearly, on the surface of that disk. Its inclination, the angle of tilt between its orbital path and that imaginary equatorial plane, is tiny, something on the order of about 1/5 of 1 degree. That is nearly nothing. That is the kind of deviation that, without careful instrumentation, you would not be able to see at all. For all practical purposes of everyday imagining, Thalassa runs a flat course, round and round the planet, as level and steady as a ball rolling in a groove. Naiad's orbit is different. Naiad's orbit is tilted, not wildly, catastrophically tilted, not cocked sideways like some rogue object tumbling in from an unexpected angle, but tilted by an amount that, given the extreme closeness of the two paths, turns out to make all the difference in the world. Naiad's orbital plane is angled at roughly 4.75 degrees away from the equatorial plane that Thalassa hugs so closely. 4.75 degrees. You could represent that angle with your thumb and forefinger held apart at a modest spread, almost nothing in any other context. But in the narrow geometry of these two near-identical orbits, 4.75 degrees is enough. It is the margin between contact and safety. It is the reason this story ends in peace. Think of it this way, if you can hold the image for a moment before you let it go and drift. Imagine two roads running side by side through an enormous open plain. The roads are almost identical in their paths, both curving gently to follow the same great loop, both keeping nearly the same pace, both running on and on through the same featureless dark. But one of the roads has been built on an ever so slight grade. Nothing dramatic, just a gentle, sustained lean to one side, rising, and then falling, and then rising again, like a very shallow wave worked into the pavement itself. The other road stays flat throughout. A traveller on the flat road, watching a traveller on the rising and falling road approach from behind, would not see someone coming straight for them. They would see someone slowly rising up above them, passing overhead, then slowly descending below, then eventually swinging back around, and doing the whole thing again. Never side by side, always either above or below. The tilt of the grade is what saves them from ever occupying the same space at the same moment. That is what Naiad's inclination of roughly 4.75 degrees does. It takes Naiad's path off the flat plane that Thalassa rides and bends it into a gentle, continuous wave, a shallow sinusoidal arc that crosses above Thalassa's level at one point in the cycle and crosses below it at another. And because both orbits remain nearly circular. Because neither moon is swinging wildly in and out on an elongated elliptical track, but rather keeping a very nearly constant distance from Neptune throughout each loop, the geometry is stable and predictable. The same crossing angle occurs at the same phase of the cycle, over and over, as reliably as a clock hand returning to the same position. Nearly circular orbits matter more than they might seem to in the calm arithmetic of this system. An orbit with significant eccentricity, one that brings a moon much closer to the planet at one end of its path and pushes it farther away at the other, introduces a kind of irregularity into the timing of encounters. The speed of a moon changes as it swings in close and then out far. The rhythm of its laps becomes uneven, unpredictable over long stretches, but an orbit that stays nearly circular keeps the moon moving at a nearly constant speed all the way around. The time per lap is steady. The rate at which Naiad gains on Thalassa, lapping it slowly, because Naiad is faster, is steady. And steady rates are what allow gravity to build and maintain the kind of precise, integer ratio lock that keeps the two moons from ever meeting at the same altitude at the same moment. Nearly circular is what makes the choreography learnable and holdable over eons, and Naiad does gain on Thalassa. This is the heart of the proximity paradox, the reason that the closeness of their paths seems so dangerous at first. Naiad, being slightly closer to Neptune, moves slightly faster, a consequence of the same orbital mechanics that govern every moon, every planet, every satellite in every system. The closer you are to the body you orbit, the harder that body's gravity pulls you forward, and the faster you must move to maintain your path. Naiad needs about 7 hours to complete one lap. Thalassa, slightly farther out, needs about 7.5. The difference is not enormous in absolute terms, less than half an hour per lap. But it accumulates. With every circuit around Neptune, Naiad finishes a fraction of an orbit ahead of where Thalassa is. And given enough time, those fractions add up, and Naiad pulls even with Thalassa. And then ahead, and eventually laps it entirely, and then pulls even with it again. This is called a conjunction, the moment when Naiad, from behind, catches up to Thalassa, draws alongside, and passes. And conjunctions, in a system where the two orbits are only about 1,850 kilometers apart, are the moments that should, by any naive reckoning, be dangerous. Two objects converging on the same patch of space, at almost the same distance from Neptune. What could go wrong? Everything. In the wrong system. Nothing in this one. Because when Naiad draws close enough to matter, when it arrives at the point where it would, on a flat orbit, be running essentially side by side with Thalassa at the same height, it is not at the same height. It is above it. The tilt of its orbit has carried it up across the equatorial plane before the moment of closest approach, so that when it finally comes abreast of Thalassa in the along-track direction, when the two moons are at their nearest, with only that narrow gap of kilometers between their trajectories, Naiad is displaced vertically by an amount that, at closest approach, comes to roughly 2,800 kilometers. 2,800 kilometers of vertical separation on top of the 1,850 or so of lateral separation. That is the real safety margin. Not just the gap between the paths, which alone is unnerving in its smallness, but the combination of that gap and the altitude difference that the tilt guarantees at the exact moment when the two are at their closest laterally. When Naiad draws alongside, it is never quite there. It is passing above, lifting over, drifting across like a shadow, moving over a hillside without ever touching the ground. And then it is past and ahead, and the gap begins to widen again, and both moons continue on their separate arcs, untroubled, but that is only the first kind of encounter. Naiad keeps lapping, and the next time it catches up to Thalassa, the next conjunction, the next moment of closest approach, the geometry has reversed. Now Naiad passes below Thalassa. Where the previous encounter sent it arcing up and over the top, this one sends it sliding down and under the bottom. Above, then below. Over the top, then under the floor. The tilt of Naiad's orbit is not a single lift in one direction. It is a wave, a continuous sinusoidal roll around the planet, so that the crossings alternate, once above, once below, once above, once below, back and forth in a measured and unhurried sequence that has been running since long before anyone was here to observe it. The vertical displacement at closest approach is roughly the same each time, about 2,800 kilometers, give or take, but the direction alternates. Up, then down. High, then low. Like a needle weaving through cloth, passing through and through and through again, without ever snagging. This is the weave. This is the motion that Naiad traces, seen from Thalassa's frame of reference, from a perspective that imagines Thalassa as the fixed point and watches Naiad approach from behind, close in, rise up and over, fall back down, and eventually swing all the way round and come approaching from behind again. From that perspective, Naiad's path is not a circle. It is something closer to a slow, long, looping zigzag, up, over the top, fall away, come around, up, under the bottom, fall away, come around. Again and again. Rising and falling, passing overhead and underfoot in alternating turns, always at a safe distance, always on its prescribed track, never deviating. Think of a hawk riding thermals over a field where another bird is resting on a low branch. The hawk spirals upward, crosses above the branch, spirals back down on the other side, and comes around again. The resting bird never moves, the hawk never lands, but every pass brings them close enough that you could, if you watched closely, see the shadow of the one crossing the outline of the other. That is the scale and the tenor of these encounters, close enough to cast a shadow, in the figurative sense, and yet never close enough to touch. The geometry provides the distance. The timing, as we will come to in the larger story, provides the guarantee. But even before we arrive at the guarantee, the geometry alone is doing something remarkable. It is converting an apparent collision course into an perpetual exchange of near misses, just by the presence of that 4.75-degree lean. 4¾ of a degree. Held in place, maintained by forces we will describe in time. Doing the quiet, invisible work of keeping two worlds apart across a span of time that makes every human timescale, every dynasty and calendar and geological era we have words for, seem brief. And speaking of the worlds themselves, we have been discussing them as points in an orbital diagram, as numbers on a chart, as positions in a sequence of encounters. It is perhaps time to spend a moment with what they actually are. Not the paths they travel, but the objects that travel them. Naiad and Thalassa are small. This is worth saying plainly, because when most of us hear the word moon, the image that arrives unbidden is something substantial, something round, something you might see hanging enormous and white over a dark field on a clear night, filling a third of the visible sky. That image belongs to Earth's moon, which is a considerable object, a world with mountains and craters and maria, and a diameter of 3,400 kilometers, visible from millions of kilometers away with the naked eye, massive enough to raise the tides of Earth's oceans twice each day. Naiad is not that. Naiad is roughly 60 to 66 kilometers across in its longest dimension, or more precisely, since it is not round, about 96 kilometers in one direction, about 60 in another, about 52 in the third, an irregular lump of material that has been described as triaxial in shape, meaning that if you took a potato and squeezed it gently into an elongated form from three slightly different directions at once, you would arrive at something vaguely resembling Naiad. Not a sphere, not even close to a sphere. An asymmetric, battered, dark little worldlet tumbling through its orbit with no particular claim to elegance in its silhouette. 60 kilometers. That is the scale of some of the larger counties in an American state, the kind of distance you might drive in a little over half an hour on an empty highway. If you stood in the center of Naiad, you would need to walk only about 30 kilometers in any direction to reach its edge, to reach the point where the surface simply curved away and the dark of space resumed. It is small enough that its gravity is a whisper, nowhere near enough to pull itself into a round shape, and small enough that it has never developed any of the geological complexity we associate with larger bodies. No volcanic activity that anyone has been able to detect. No weather. No interior warmth to speak of. Just a lump of rock and ice and ancient material, dark and quiet, going around and around in the cold. Thalassa is slightly larger, though in the same general category of smallness. Its dimensions run to about 108 kilometers in one direction, about 100 in another, about 52 in the third, similarly irregular, similarly potato-shaped by the same gentle definition. Its widest extent is perhaps 80 to 82 kilometers across, depending on how you slice it. Two rocky, battered, dark, small bodies, one slightly bigger than the other, both tiny by any standard that a moon is usually expected to meet. If you placed Naiad and Thalassa side by side in the open landscape somewhere on Earth, they would each fit comfortably within the bounds of a modest metropolitan area and its surrounding countryside. You could walk around either of them in a day, if the gravity were kind. They are also dark. Darker than you might expect, darker than a moonlit night already is. Their surfaces reflect only a small fraction of the light that falls on them from the distant sun. somewhere in the range of perhaps 7 to 10%, a value astronomers call albedo. For context, fresh snow reflects roughly 80 to 90% of the light that hits it. Dry concrete reflects about 30%. Thalassa and Naiad reflect something closer to what old worn charcoal reflects, a deep, unreflective darkness, soaking up almost everything that arrives and giving back very little. The cause of this low albedo is not entirely resolved, but it is consistent with surfaces that have been processed for a very long time by radiation, by micrometeorite impacts, by the steady chemistry of a cold and dark environment, potentially rich in carbon compounds that do not scatter light so much as absorb it. They are the colour, in the fullest sense, of an old shadow. Out there in the near darkness of the Neptunian system, where sunlight is already roughly 900 times fainter than what falls on Earth at noon, where the sun itself, blazing at the centre of the solar system, appears from Neptune's distance as a merely bright star rather than as the overwhelming presence we know from our own sky. Out there, Naiad and Thalassa are almost invisible against the black. They neither gleam nor glow. They move through their orbits in the deep quiet of a twilight that never changes, unreflective and almost featureless, identifiable mainly by their motion, by the tiny, steady arc they trace against the background of stars as they swing around the planet. And they carry names that belong to the world of water, which is a lovely, perhaps poetic accident of the convention that ties this corner of the naming catalogue to the sea. Neptune, the planet, takes its name from the Roman god of the sea, the divine sovereign of the deep waters. It follows, then, that the tradition governing the naming of Neptune's moons borrowed from the same mythological neighbourhood. Naiad, the name given to the innermost of the two, comes from the Greek Naiad, which denotes a freshwater nymph, a minor deity associated with rivers and springs and lakes, the kind of being the ancient Greeks imagined inhabiting every stream and pond and underground source of water, presiding gently over the places where fresh water moves through the world. The Naiads were quiet, local presences, not the great gods of Olympus, but the small, intimate guardians of the living places where people came to drink and wash and rest. Thalassa's name comes from an older tradition still. Thalassa, in Greek, is simply the sea itself, the primordial personification of the salt water that surrounded and preceded everything in the cosmology of the ancient world, the raw ocean before it was given a ruler, before Poseidon took his trident and claimed dominion. Thalassa was not a god so much as an elemental force, one of the first things to exist, the sea as a being rather than a body of water. To call a moon Thalassa is to give it the name of something ancient and vast and foundational, something that was there before the stories of gods had even begun. Two water beings circling the sea god's planet, in the dark and the cold of a place so distant that the light reaching them from their home star is barely enough to read by. There is something fitting about this, even if the fittingness is largely our own invention, a pattern we have draped over the orbital mechanics for the comfort of feeling that things have been named well. But the names are not merely decorative. They carry in them a faint record of the human tradition that sent a spacecraft out to this system and then went carefully about the work of understanding what it found. The naming of moons is one of those small rituals by which science and mythology briefly touch, the careful, systematic work of orbital measurement and photometric analysis resting for a moment against the old stories of the Greeks. Before the work resumes and the names become simply labels for objects at such and such a distance, moving at such and such a speed. in such and such an arrangement relative to one another. And the arrangement these two water beings have found for themselves, or rather the arrangement that gravity has settled them into over a vast span of time, is the thing that remains extraordinary. The thing that the names and the darkness and the smallness and the coldness are all just context for. The arrangement is the point. The tilt, the weave, the closeness that is not, somehow, danger. Naiad at 48,200 kilometers. Thalassa at 50,000. The gap between them, about 1,850 kilometers. Naiad inclined at roughly 4.75 degrees, while Thalassa runs nearly flat. Both orbits nearly circular, holding their shapes steadily through each lap. Naiad gaining on Thalassa slowly over hours, and when it catches up, rising above by about 2,800 kilometers at closest approach, and then, next time, sliding below by about 2,800 kilometers again, up, then down, over and under, weaving through the space beside its neighbor without ever meeting it at the same height. All of that is the geometry. All of that is the physical arrangement, the positions and tilts and paths that you could, in principle, measure and verify and draw on a diagram. And all of it is remarkable enough on its own. But the geometry alone does not fully answer the question. It tells you what the two moons are doing at any given moment, rising over or sliding under. But it does not tell you why they are always doing it safely, why the encounters always happen when Naiad is displaced, when it is above or below rather than at the exact same level as Thalassa, why the timing never slips, why Naiad does not, on some conjunction, arrive alongside Thalassa at the wrong phase of the wave, not above, not below, but exactly even, and close the distance to zero. The answer to that is not in the geometry, it is in the numbers, in the exact count of the orbits, in the ratio, a very particular, very precise integer ratio that governs how many times each moon goes around before the pattern repeats. And that ratio is where the real story lives. The story of how gravity, left to work across long enough timescales, teaches two worlds not just how to pass each other safely once, but how to do it the same way, at the same phase, in the same safe configuration, forever. That story is waiting. We will reach it. But first, before we move toward the numbers and the ratio and the long, patient arithmetic of orbital resonance, let us sit for just a moment longer with the simple picture. Two dark, small, irregular worlds, spinning slowly as they go, orbiting Neptune in an almost shared path that brings them, over and over, into a closeness measured in something less than the width of the western United States. And every time they come close, one of them is never quite where you might expect it to be. It is up, or it is down. It is displaced by the lean of its track, carrying the safety of that 4.75 degree tilt like a quiet guarantee written into the structure of its path. The tilt is not dramatic. It is not the kind of thing that announces itself. If you could somehow hover in the Neptunian system and watch these moons pass each other, you would not see a spectacular avoidance maneuver, a visible sudden swerve, a gap opening dramatically at the last moment. You would see two small dark shapes, one crossing the path of the other at a gentle angle, at a leisurely and unhurried pace, in a silence so complete that no word for silence in any human language quite captures it. You would watch one rise over the other slowly enough that you might almost miss it, and then recede. And you might not, at first, understand that what you were watching was a system of extraordinary precision, not silence, but order, not emptiness, but careful arrangement. The tilt is the quiet engineering. The tilt is the built-in margin. And within that margin, the weaving happens up, over, down, under, up, over, down, under, as regularly as breathing, as regularly as the turning of a tide. Naiad does not deviate from it. Thalassa does not flinch. The geometry holds, the paths remain clear, and somewhere in the cold dark around Neptune, two potato-shaped lumps of ancient, dark material exchange their silent, tilted near misses and go on. I find, sometimes, that the word choreography is used for things like this. For the motions of moons and planets in their complex and mutually arranged paths. It is a word borrowed from dance, from the deliberate design of human movement, and it carries in it an implication of intention, of someone having planned the steps. No one planned these steps. No mind arranged the tilt of Naiad's orbit or set the phase of its encounters with Thalassa. The choreography here emerged, worked its way over an enormously long span of time into the only stable configuration that gravity in this particular geometry with these particular masses and speeds could hold. The dance is not designed, it is found, it is the pattern that survived. That distinction, I think, is part of why it is calming rather than merely impressive. If someone had arranged this, you might wonder whether they might also rearrange it, whether the plan might change, whether the choreography might someday be revised. But a pattern that gravity found on its own, a pattern that represents the lowest available energy, the most stable reachable configuration, the arrangement that has already survived whatever challenges the long history of this system has offered, that is a different kind of permanence. It is not kept in place by intention. It is kept in place by the same forces that have been operating since the solar system formed. It is self-maintained, self-correcting, resistant to small disturbances, in the same way that a ball resting at the bottom of a bowl is resistant to small disturbances. Nudge it, and it returns. Not because someone nudges it back, but because the shape of things requires it. The shape of things around Neptune at this particular distance requires Naiad and Thalassa to pass each other safely. Not sometimes, not usually, every single time. And that requirement, the mechanism behind it, the arithmetic of orbits that makes it not just likely but guaranteed, is the piece of the story we have been slowly making our way toward. The piece that Mark Showalter and his colleagues at the SETI Institute spent years working out from Hubble data. The piece that sits behind the tilted track and the over and under weave and makes the whole arrangement not just beautiful but airtight. We are nearly there. The numbers are waiting, steady and quiet, the same now as they were when Voyager 2 made its single, brief, astonishing pass and left us with two faint points of light labelled N5 and N6 and decades of wondering. The same as they will be on whatever night comes after this one, and the one after that, and the long sequence of nights unspooling quietly out ahead. Let the image sit with you as you settle. Two small dark moons, tilted and flat, close and safe, weaving their slow alternating passes in the near dark of a system 4.5 billion kilometers from the warmth of the sun. The wave rising and falling and rising again. The gap always open, the passing always clean, every approach dissolving into a safe and unhurried departure. There is, in that image, something that asks very little of you. It does not need your attention to continue. It does not need your vigilance or your worry. It has been going on without any of that for longer than the first human word was spoken, and it will continue without any of that long after the last one. The only thing required, here at this distance, tonight, is to notice it. To hold it briefly, the way you hold a smooth stone from a riverbed, its weight familiar and uncomplicated in the palm, and then to let it rest. Naiad, rising Thalassa, steady in its flat and quiet path. The gap between them, 1,850 kilometers of empty space, and a little over 2,800 more of altitude. Both small, both dark, both ancient, in their way, both going around. And the reason that closeness is safe, the reason the near miss always resolves, waiting just a little further along in the dark, in the exact count of their laps, in a ratio that gravity locked in place and has been keeping ever since. Rest easy, if you can. We are not in a hurry. The moons are not in a hurry. Everything here proceeds at its own measured pace, in good order, with nothing left to chance. That ratio, when you first hear it stated plainly, sounds like something a mathematician might write on a piece of paper and then set aside, unremarkable at first glance. A pair of numbers sitting beside each other with no obvious drama in them. 73 to 69. And yet those two numbers and the relationship between them are the whole of the reason that this dance continues. They are not decorative. They are not approximate. They are the count, the exact count, that gravity settled on when it arranged the timing of these two small moons, and they are what transforms a near collision into something as reliable and as calm as a clock. Here is what that count means in practice. Imagine you are watching from somewhere above the plane of Neptune's equator, looking down on both moons as they travel their separate circles around the planet. Thalassa is a little further out, its orbit flat and nearly circular, and it moves a little more slowly because of that extra distance. In the same way that a runner on the outer lane of a track has to cover more ground with each lap and cannot, even at the same speed, keep up with someone running the inner lane. Naiad is on the inner lane, closer to Neptune, and it moves faster, and so over time it slowly gains on Thalassa, lap after lap, the gap between them closing gradually until Naiad has circled around to where Thalassa is and then passed it and pulled ahead. That passing, that moment of near approach, is what could be dangerous. Two moons, almost the same distance from their planet, passing each other in the same general neighborhood of space, separated by a gap that on solar system scales is almost nothing. But now add the count. For every 69 full orbits that Thalassa completes, Naiad completes exactly 73. Not approximately, not roughly, exactly, in the way that a key exactly fits a lock, in the way that a gear exactly meshes with its counterpart. The number is precise and sustained, and it means something very specific, that every time Naiad catches up to Thalassa and draws close, the geometry of their positions, their relative locations in their respective orbits, is not random, it is fixed. The phase of Naiad's tilted orbit, how far through its up and over and down and under cycle it happens to be at that moment of closest approach, is always the same. And the orientation that tilt places Naiad in, at that locked and precise moment, is always displaced. Always safely to one side, always either well above or well below the flat orbital highway that Thalassa travels. The count is the mechanism. The ratio is the safety. It is, when you sit with it, a rather beautiful piece of arithmetic. Not beautiful in any abstract sense, not beautiful as a theorem written on a blackboard, but beautiful in the way that a solution is beautiful. A problem that could have gone badly and found instead an answer that holds. Two moons, close enough that the gap between them looks, on any reasonable diagram of the solar system, like almost nothing, and they hold that closeness through a number. 73. 69. A rhythm that locks them into perfect mutual avoidance, repeated without variation, sustained without effort, maintained by the same gravity that holds the whole system together. Orbital resonances are not rare as celestial arrangements go. The solar system is full of them, this tendency of orbiting bodies to fall into step with one another, to count out their laps in simple integer ratios. Jupiter's moons Io, Europa, and Ganymede are locked in a 1:2:4 resonance that has persisted for billions of years. For every one time Ganymede goes around Jupiter, Europa goes around twice, and Io goes around 4 times. A synchrony so stable it has shaped the inner structures of all 3 worlds, stretching and squeezing and heating them with tidal friction. Pluto and Neptune themselves share a 2:3 resonance, so that Pluto, despite crossing Neptune's orbit, never comes close to Neptune, because the timing of their encounter is always arranged to keep them apart. The universe, at every scale, seems to prefer these locked ratios, seems to find its way toward these whole number relationships the way water finds its way downhill. Not through intelligence, not through intention, but through the simple geometry of what lasts. What Naiad and Thalassa share, though, is not the ordinary kind. The resonance between them was characterized by those who worked it out as a first-of-its-kind arrangement, a fourth-order resonance, in the technical language of orbital dynamics, a type not previously catalogued in this exact form for any known pair of moons. To understand what that means, and to understand why it matters, it helps to think about what an orbital resonance is doing, mechanically, at any given moment. When 2 orbiting bodies are in a simple resonance, a 1:2 or a 2:3, every encounter between them happens at a location in their orbits that is nudged, slightly, by the other body's gravity. The nudge is small, but it accumulates, and over time it shapes the orbit, reinforcing certain patterns and suppressing others. The order of the resonance describes how complex the interaction between those nudges is. How many different periodic cycles are overlapping and contributing to the final result. A fourth-order resonance is more intricate than a first- or second-order one, more finely tuned, more specific to the exact orbital conditions that produced it. And those orbital conditions, for Naiad and Thalassa, are unusual enough that the combination of their exact orbital spacing, their exact speeds, and Naiad's exact tilt apparently produced something the catalogues of known moon resonances had not contained before. Not impossible, the physics that generates it is the same physics that generates every other resonance in the solar system, but specific. A particular arrangement that required the precise values this pair of moons happened to have settled into, and that generates precisely the kind of protection they need, not just a timing lock, but a timing and tilt lock, one that synchronizes the count of their laps with the phase of Naiad's tilted weave, so that every close approach lands Naiad in the right position relative to its up and down. Cycle to pass safely over or safely under, never alongside. First of its kind is a phrase that scientists use with care. It does not mean impossible, and it does not mean there is nothing else like it anywhere in the universe, in the countless other planetary systems we have not yet examined closely enough. What it means, here, is that in all the moons of all the planets that we have studied with enough precision to characterize their orbital relationships, this particular arrangement had not been seen. Naiad and Thalassa, 2 small dark worldlets orbiting a planet no spacecraft, other than Voyager 2, has ever visited, turned out to be doing something genuinely novel, a new entry in the catalogue of the ways that gravity can keep things safe. There is something in that worth holding for a moment. The solar system has been here for about 4.5 billion years. Human beings have been observing the sky with care for a few thousand of those years, and with instruments sensitive enough to detect orbital resonances for perhaps a few hundred. In all of that time, in all of those measurements, this specific kind of dance had not been identified. It was waiting in a place where we had only ever looked once, briefly, for a few hours, from a spacecraft that was already moving on toward the outer dark. And it waited there, Naiad and Thalassa going around and around in their locked 73 to 69 count, unremarked and uncharacterized until the instruments finally came that were precise enough to see it. But that is, in its way, the story of almost everything we know about these two small moons. The story of how their dance was discovered is itself a story about patience, about returning to something seen only briefly, about looking more carefully than anyone had yet managed, and finding that the careful look revealed something the quick one had missed. Voyager 2 in August of 1989 gave us the moons. It did not, could not, give us the dance. Think about what a single flyby means in practice. Voyager 2 was moving at tremendous speed, it had to be, to reach Neptune after a 12-year journey from Earth, and its closest approach to Neptune itself lasted hours, not days. The encounter was extraordinary by any measure, a single human-made object threading through a planetary system never before visited. Its cameras and instruments running continuously, capturing images and data at every opportunity. It was during those hours that the existence of Naiad and Thalassa was first established, their small dark shapes turning up in the images as points of light. New moons added to the count of what Neptune kept close to itself. Naiad received the provisional designation S1989N6. Thalassa was S1989N5. Names that were, for the moment, just labels on new discoveries, placeholders until something more could be understood about each of them. And then Voyager 2 was past Neptune and heading outward, and the solar system's most distant planet was once again a bright blue dot in the distance, growing smaller, returning to the kind of remoteness that had always defined it. The moons it carried close to itself, Naiad, Thalassa, the others, were back in the dark, beyond the reach of any instrument then capable of watching them closely enough to understand what they were doing. The moons orbited. The resonance kept them safe, as it had before, as it continued to, as it always would. But nobody, for a long time, was watching precisely enough to see it. What Voyager gave us was position, where each moon was, roughly, at the moment the spacecraft passed by. From that, and from the basic orbital mechanics that govern how fast something at a given distance from a planet must be travelling, it was possible to estimate orbits, to extrapolate where Naiad and Thalassa and the others would be in the future. Those estimates were good, in the way that first measurements often are, good enough to confirm the basic picture, to know the approximate sizes of the orbits and the approximate periods, to know that Naiad was slightly closer and slightly faster, and that Thalassa was a little further out and a little slower. But they were estimates, and for the subtler geometry, the precise tilt, the precise ratio of their orbital periods, the exact phasing of their encounters, the data from a single quick flyby was not sufficient to reveal what was really happening. To see the dance, you needed to watch the moons over time, through many orbits, with instruments sensitive enough to track tiny, dark, distant objects against the overwhelming brightness of a planet that is, even from Earth's instruments, not especially easy to study. You needed to be patient in a way that a flyby simply cannot be. The instrument that eventually made it possible was the Hubble Space Telescope. Hubble, in orbit above Earth's atmosphere, has advantages that ground-based telescopes cannot fully match. The atmosphere blurs and distorts light passing through it, limiting how precisely anything beyond the sky can be measured. Remove the atmosphere from the equation, and the measurements become cleaner, more consistent, more amenable to the kind of careful, repeated observation that reconstructing a distant orbit requires. Hubble cannot travel to Neptune. It orbits only a few hundred kilometers above Earth's surface, a location that by the scales of the outer solar system is essentially standing still. But it can watch. And it can watch repeatedly, and over time a collection of careful watches can add up to something a single snapshot never could. The work of making sense of what Hubble showed about Naiad and Thalassa was led by Mark Showalter, a planetary scientist at the SETI Institute, and it was demanding work in ways that are worth pausing over. Thalassa is extraordinarily difficult to observe. It is small, no more than about 80 or 82 kilometers across. A worldlet you could drive across in well under an hour if there were any road and any atmosphere to do it in, and it is dark, reflecting perhaps 7 or 10% of the light that reaches it, surfaces of something that may be carbon-rich and ancient, absorbing almost everything the weak Neptunian sunlight offers. And it orbits close to Neptune, which means that from any distance, the glare of the planet itself washes over the region where Thalassa lives, making it harder to isolate the tiny, dim point of light that is the moon from the far brighter wash that is the planet. To track Thalassa precisely enough to reconstruct its orbit, the team had to work carefully through multiple Hubble observations, accounting for the planet's brightness, managing the noise and the uncertainty that comes with imaging something so small and so faint at such a distance. It was painstaking. It required returning to the data again and again, comparing measurements across observations separated by time, building up a picture incrementally that no single image could have given. Naiad presented a different challenge, and in some ways a stranger one. After Voyager 2 had passed, and after the initial excitement of the 1989 discoveries had settled into the quieter work of cataloguing and understanding them, attempts were made to observe the new inner moons from Earth and from the Hubble Space Telescope. Thalassa could be tracked, with effort. Some of the other inner moons could be followed. But Naiad proved elusive. The moon that Voyager had found, that existed without question in the 1989 images, that had been provisionally designated and noted and catalogued, that moon simply could not be reliably found when astronomers looked for it afterward. It was not where the extrapolated orbit said it should be, or the uncertainty in the extrapolated orbit was too large to know if it was there at all. Or it was simply too faint and too close to Neptune to be separated from the background. For years, Naiad was a moon that existed in the record, there, unambiguously, in the 1989 images, and could not be confirmed anywhere else. A moon, in other words, that was lost. Not lost in any dramatic sense, not gone, not destroyed, not knocked out of its orbit by some subsequent collision. Lost in the observational sense, the cartographic sense. The map said it was somewhere in this general region, but the instruments, when aimed at that region, could not find it with confidence. This is a stranger feeling than it might sound once you sit with it. There is an object, a real object, made of rock and dark material, 60 or 66 kilometers across, orbiting the innermost position of all of Neptune's regular moons, completing a full orbit every 7 hours or so, tens of thousands of kilometers per hour, and it simply could not be located. The solar system had swallowed it, not into any void, but into its own difficulty. A planet too bright, a moon too dark, a distance too immense, a window of observation too brief. And then, gradually, carefully, in observations made with Hubble after enough time had passed, and the data had been refined, and the tools for managing the difficulty had improved, Showalter's team found it again. The recovery happened around 2004. Not a dramatic rediscovery in any headline sense, no moment of a new light appearing where none had been expected, no sudden flash of confirmation. More like the gradual clarification of something that had been uncertain, a probability that resolved into confidence as the data accumulated. The orbit, worked out from the new observations, was refined, and the measurements began to show not just where Naiad was, but how its orbit was actually oriented, and the picture that emerged, when compared carefully with what Thalassa's orbit was doing, was more intricate than anything the early 1989 data had suggested. The dance was there in the numbers, if you looked carefully enough. It took the 2019 analysis to make it fully clear. The team led by Showalter, working with the full accumulation of Hubble data that had been gathered over years, published their findings in the journal Icarus, a name that carries its own quiet irony in the context of a story about something that did not fall, that did not come too close, that found instead the safe path and held it. In that paper, the orbital resonance was characterized in detail, the 73:69 ratio, the fourth-order nature of the interaction. The way Naiad's inclination of about 4.75 degrees was not incidental to the resonance, but central to it, part of what made this particular type of lock possible. The dance was not a coincidence observed after the fact and called a resonance by analogy. It was, the analysis showed, a genuine orbital resonance in the technical sense, a specific, stable, mathematically characterizable configuration that gravity had settled the two moons into and was actively maintaining. That word, maintaining, is the one worth slowing down on. It might be tempting to think of the 73:69 lock as something that happened once, long ago, when the moons first settled into their current orbits, and has simply continued by inertia ever since, the way a coin set spinning on a table keeps spinning until friction stops it. But orbital resonances do not work by inertia. They work by continuous reinforcement. What keeps Naiad and Thalassa locked in their ratio is not that they reached it and then coasted, it is that every time their orbits nudge slightly away from the ratio, the gravitational interaction between them nudges them back. Each close pass, each moment of near approach, involves a tiny exchange of gravitational influence, Naiad pulling on Thalassa ever so slightly, Thalassa pulling on Naiad. And the geometry of the resonance ensures that those pulls, accumulating over time, always act to restore the ratio rather than to disrupt it. The lock is self-reinforcing. The choreography is self-sustaining. Think of it as something like the way a metronome keeps time. The pendulum swings, and if it strays slightly from its rhythm, the mechanics of the pendulum bring it back. The restoring force is built into the system. You do not need to watch it and correct it manually. You do not need to intervene every time it drifts. The system tends toward its rhythm on its own, and deviations are damped rather than amplified. In an orbital resonance, gravity plays the role of the restoring force. The moons cannot easily leave the resonance because doing so would require overcoming the accumulated effect of their mutual gravitational nudges, which are all pushing, in their quiet and distributed way, back toward the lock. This is not luck. This is the word that must be said clearly, because the distinction matters. If you heard only that Naiad and Thalassa have been passing each other safely for a very long time, you might reasonably suppose that this was a fortunate coincidence, two moons that happened, by chance, to have orbits that do not quite intersect, and so have kept their distance by accident, by the absence of any specific mechanism that would bring them together. That is not what is happening. There is a specific mechanism, and it is working continuously, and it is working in the direction of keeping them apart. The tilt of Naiad's orbit, the precise ratio of their orbital periods, and the mutual gravitational interaction between the two moons are not independent features that separately happen to produce a safe outcome. They are a coupled system, a single dynamical arrangement in which each element supports the others. The tilt makes the resonance of this type possible. The resonance locks the timing of the close passes to the phase of the tilt. The mutual gravity reinforces the resonance against perturbations. Remove any one element, and the system would be different. Together they produce something that is stable, consistent, and self-perpetuating. A problem that found its answer. An answer that keeps itself. The people who worked this out, Showalter and his collaborators at the SETI Institute, using data from a space telescope that was itself a story of careful human persistence and patience and the willingness to return to a problem over decades, did not have the advantage of watching the dance unfold in anything resembling real time. They reconstructed it from measurements, from positions of small dark moons recorded at different moments across years of Hubble observations, feeding those measurements into the mathematics of orbital dynamics until the picture resolved. It is a particular kind of knowledge, the knowledge of something inferred rather than directly witnessed, built up not from a single observation, but from many, each one contributing a small piece to a larger pattern that becomes visible only when enough pieces are in place. There is something patient about that kind of knowing, something that does not demand immediate clarity but is willing to accumulate evidence slowly, to let the picture come into focus at its own pace, to wait through years of data gathering for the moment when the numbers finally resolve into something that makes the geometry visible and the mechanism plain. The universe keeps its deeper workings at a distance, in every sense, spatially, at 4.5 billion kilometers from the instruments that read them, and temporally, in the decades between the first glimpse and the full understanding. To learn what Naiad and Thalassa are doing, it was necessary to be as persistent as the moons themselves. And Naiad, specifically, required that persistence twice. There is something gently humbling about the fact that one of the two protagonists of this particular story was, for a significant stretch of time, simply missing from the calculations, present in the record, absent from the follow-up, a moon that everyone knew existed and nobody could find. It was not that astronomers forgot about Naiad or decided it was unimportant. It was that the combination of its small size, its dark surface, its close proximity to Neptune's overwhelming brightness, and the limitations of the instruments available made the moon harder to track than the initial discovery had suggested. The orbit predicted from the 1989 Voyager data was imprecise enough that later searches could not confidently identify Naiad against the noise, and so it remained in a kind of observational limbo, a confirmed moon that could not be confirmed again. The recovery, when it came, required not just better images but better analysis, more sophisticated methods of filtering out Neptune's light. More careful comparison of positions across multiple observations, more refined orbital modelling, that could take the constraints from Hubble's data and narrow down where Naiad must actually be, rather than where the early estimates had guessed. It required, in other words, the kind of effort that produces not a dramatic discovery, but a quiet resolution. The moment when the numbers finally settle and the uncertainty collapses into confidence, and the thing that was lost turns out to have been there all along, going around and around at nearly 48,000 kilometers from Neptune's center, completing its 7-hour lap, rising and falling in its tilted circuit, waiting with the patience that small dark moons in the outer solar system apparently have in abundance. The recovery around 2004 was the prerequisite for everything that followed. Without knowing with precision where Naiad's orbit actually was, its exact tilt, its exact radius, its exact period, the comparison with Thalassa's orbit that would eventually reveal the resonance could not be made. The 2004 recovery was a restoration of information that the 1989 flyby had initiated but not completed, and it was only once that information was in hand, and then refined further across the following years of Hubble observation, that the full picture of the 73 to 69 dance became visible. So the discovery has a shape. 1989 first sees them. 1989 to 2004 loses one. 2004 finds it again. 2004 to 2019 accumulates the orbital data. 2019 makes the mechanism plain. 30 years from the first glimpse to the full understanding. The moons, in that time, completed somewhere on the order of 31 million laps around Neptune. They ran their ratio without variation through all of those laps, through all of that time, through all of those years when no instrument precise enough to see what they were doing was pointed in their direction. They did not need anyone to know about the dance in order to keep dancing. The resonance does not require observation. It required, in the end, the journal Icarus and the team led by Showalter at the SETI Institute to give it its name. But the dance itself predated the naming by a very long time, and will continue long after any particular paper has faded from the active literature into the archive. What is the feeling of that, if you sit with it quietly? A thing kept going, without witness, in the near dark at the outermost edge of the planetary solar system, not waiting to be seen, not requiring validation, just going 73, 69, 73, 69, in the measured and unhurried way that gravity arranges these things, in the cold and the darkness and the almost silence of a place where sunlight is a faint and distant thing, and the nearest other planetary system is still an incomprehensible distance further out. The dance does not need you. It does not need anyone. It does not need acknowledgement in any journal or database or neatly typeset table of orbital elements. It is the thing itself, undisturbed, proceeding according to the rules by which the universe runs, with no interest in whether or not it is understood. There is something restful in that, not the restfulness of emptiness, not the restfulness of blankness or absence, the restfulness of a system that has found its answer and is simply running it, continuously, reliably, without pause, without error, without any of the anxious monitoring that might accompany something less stable, less self-sustaining, less thoroughly worked out. Naiad rises, and Thalassa continues in its flat and steady circuit, and the separation between them, at closest approach, is about 2,800 kilometers of altitude, safe, geometrically guaranteed, maintained by the count. And then Naiad descends, and the next approach comes, and the geometry repeats, and the count locks it safe again, and again, and again. The SETI Institute, where Showalter works, has its mission in the study of the origins and nature of life in the universe. A large and patient question, one whose answer has not yet been found, one that requires exactly the kind of accumulated careful observation and refined analysis that the Naiad recovery and the resonance discovery also required. That the same team, in the same 2019 publication, also found Hippocamp, a seventh inner moon, a small chip of rock about 35 kilometers across. Orbiting near Proteus, apparently a fragment knocked loose from Proteus by some ancient comet impact and now keeping its own quiet orbit in the same crowded inner neighborhood, suggests something about the nature of this kind of work, that the careful looking, the patient accumulation of data, the willingness to build a picture over years rather than demanding it in an afternoon, tends to find more than it was specifically looking for. The 2019 Hubble analysis of Neptune's inner moons gave back the full choreography of the dance between Naiad and Thalassa, and also gave back a new moon, and both came from the same deep, careful attention to a place that had not been closely looked at in 30 years. Patience, here as elsewhere, finds things that impatience walks past. And what those 30 years of patient looking gave back, in the end, is a picture that repays any time you spend with it. Two small dark moons, no wider than a modest mountain range is long, riding orbits separated by less than the distance across a moderately large country, going around a cold blue planet in 7-hour loops, maintaining through their mutual gravity a lock so specific and so stable that it has been characterized as a first of its kind among known satellites, and doing all of this in the near dark, in the near silence, in a place where the sun is a bright star rather than a warm presence, and where the nearest any human-made object has ever come was a single passage of a spacecraft that had been travelling for 12 years and would not linger. The dance was there before anyone named it. It will be there long after. And the number at its heart, 73 to 69, repeated for every orbit, maintained by the choreography of two small worlds and the quiet authority of their mutual gravity, is one of those numbers that earns its elegance not by being dramatic, but by being exact. By being the right number, by being the count that, given the tilt and the spacing and the speeds involved, produces not a collision but a clean pass, not a crash but a continuation, not an ending but another circuit, and then another after that, and then another, in the dark and the cold and the vast unhurried patience of a system that has found what it was looking for and does not need to look again. 73. 69. Rising, falling, safe. But the dance does not exist in a vacuum, and if you have been resting with it long enough tonight, it is worth knowing where it came from. Not because the origin changes anything about the beauty of what Naiad and Thalassa are doing right now. In this moment, as you lie still, they are still threading past each other, still rising and falling in their locked 73 to 69 rhythm, still maintaining the small vertical distance that keeps them whole and separate and safe. The origin does not alter the present, but it deepens it, the way knowing something about the history of a house you love changes the feeling of being inside it, makes the walls hold more meaning, makes the quiet feel earned rather than simply given. And what happened here, in the deep past of this cold blue system at the edge of the solar neighborhood, is something that has no gentler word for it than catastrophe. Neptune, at some point in the early life of the solar system, had a moon system of its own. Not the moon system it has now, but an original one. A set of satellites that formed the way moons are expected to form. condensing from the disk of material that orbited the planet in the early chaos of planetary assembly, settling into orderly prograde orbits, that is to say, orbiting in the same direction as Neptune's own rotation. The way most moon systems organize themselves, the way Earth's moon orbits, the way the large moons of Jupiter and Saturn orbit. An ordered, reasonable arrangement. Moons going around their planet in a coherent family, each on its own path, each at peace with its neighbors. And then something arrived. What arrived was Triton. And Triton did not arrive politely. Triton is Neptune's largest moon by a margin so vast it makes the comparison almost absurd. It is roughly 2,700 kilometers across, making it larger than Naiad and Thalassa combined and then multiplied by a number that is difficult to say casually. It is, in the accounting of the solar system, a genuinely large world, larger than Pluto. Large enough that if it orbited the Sun independently rather than Neptune, it would be classified among the notable bodies of the outer solar system. And the leading model, the one that the evidence most strongly supports, is that Triton was not born at Neptune. It did not condense from the disk around Neptune. It came from somewhere else entirely. It came most likely from the Kuiper belt. The Kuiper belt is that vast, cold, ring-shaped region of the outer solar system that lies beyond Neptune's orbit, a reservoir of icy bodies, frozen remnants of the early solar system that never assembled themselves into a full planet, orbiting in the dark at immense distances from the Sun. Pluto lives there. Thousands of smaller objects live there, each moving in its own cold ellipse, minding its own long, slow circuit. Triton, the thinking goes, was once one of them, a substantial Kuiper belt object. A world of ice and rock drifting in the outer dark, until the geometry of the solar system's early turbulence brought it close enough to Neptune that Neptune's gravity caught it, captured it. The word sounds clean, almost gentle, like something placed carefully in a container. But a gravitational capture of a body the size of Triton by a planet the size of Neptune would not have been a quiet event for anything already living in that system. A moon-sized intruder falling into a steep, irregular orbit around Neptune. Its path not the calm circular track of a native satellite, but a wildly elongated, looping thing. Crossing through the orbits of every moon that was already there, that is a disruption of a kind that does not leave the furniture where it was. The mathematical models suggest that the gravitational interactions generated by Triton's capture would have been severe enough to scatter, destabilize, and likely destroy most of whatever original satellite system Neptune had assembled. Moons that had orbited quietly for hundreds of millions of years would have been flung out of their paths, sent careening into new orbits, colliding with one another, breaking apart, leaving behind clouds of debris that would take immense spans of time to reassemble into anything resembling a stable family again. So the moons we see today, the inner small moons of Neptune, Naiad, Thalassa, and the other small bodies orbiting close to the planet, are not survivors of that first arrangement. They are, by the best current understanding, second-generation objects. They are reassembly. They are what happened when the debris from that ancient catastrophe slowly, over millions and millions of years, came back together under the influence of gravity, clumping, merging, compressing, until these small, dark, potato-shaped worlds condensed out of the rubble and settled into their new orbits, going around a planet that had, by then, finished absorbing most of the shock of its great intruder. The catastrophe had happened. The planet had survived it, and in the settling quiet that came afterward, in the gradual reorganization of the material that Triton's arrival had scattered, these moons were made. Which means the dance that Naiad and Thalassa are performing right now, that 73 to 69 weaving rhythm, the tilted track, the reliable over and under passage every few hours in the dark, all of it is a product of that violence. All of it emerged from wreckage. The peace that exists tonight in those two small orbits is not a peace that was simply given at the beginning and maintained without effort. It is a peace that was built over timescales that make the age of human civilization look like a single afternoon, out of the material of something that was destroyed. It is order that came from disorder, rhythm that came from chaos, a stable dance that assembled itself from the scattered remnants of a system that was broken apart by an enormous wandering world that fell in from the dark edge of the solar system a very long time ago. There is something in that, if you let it settle. Triton itself is still there, of course, still orbiting Neptune, and it orbits to this day in a way that announces its outsider origin as clearly as anything in the solar system. It orbits backward. Every other substantial moon in the solar system, with a very few exceptions, orbits in the prograde direction, in the same direction as its planet's rotation, following the natural momentum of the disk from which the planet and its native moons formed. Triton orbits in the opposite direction, retrograde, circling Neptune from east to west, while Neptune turns from west to east, beneath it, the largest known moon anywhere in the solar system, to do this. It is a permanent, unhurried declaration that it was not born here, that it came from elsewhere, that it arrived as a foreign body and was taken in, and that its presence reshaped everything close to the planet it now calls home. When you think about Naiad and Thalassa riding their tiny linked orbits in the near darkness near Neptune's equator, it is worth letting that context settle around them. These are not ancient original bodies that have been quietly going about their business since Neptune first formed. They are younger than the catastrophe. They are made from the aftermath. They came after. And somehow, in the long, patient process of reassembly, they found each other's timing, settled into the orbital configuration that the geometry and the physics allowed, and ended up in this locked dance, this first-of-its-kind resonance, this tilted track that keeps them safe. Not despite the violence that preceded them, but, in a sense, because of it. The destruction cleared the space, the slow rebuilding found the stable configuration, the catastrophe, over time, became the choreography. And Naiad and Thalassa are not alone in this small inner family. There are other moons in the neighborhood, other bodies that came from the same rubble and settled into their own orbital arrangements close to Neptune. There is Despina, and there is Larissa, and there is Proteus, which is the largest of the inner moons and substantially bigger than its neighbors, a roughly irregularly shaped world a few 100 kilometers across. All of them assembled from the same material, all of them living in the same cold, faint lit space close to the planet. And then there is Hippocamp. Hippocamp is the smallest of the known inner moons, roughly 35 kilometers across, smaller even than Naiad, smaller by a meaningful amount, and it was discovered by the same team, led by Mark Showalter of the SETI Institute, using the same Hubble Space Telescope images, and reported in the same year, 2019, though its finding was published in the journal Nature rather than the Icarus paper. That described the Naiad-Thalassa resonance. Two discoveries in one body of work, two pieces of this quiet, dark, cold moon family revealed in a single careful analysis. What makes Hippocamp remarkable, beyond its smallness, is where it apparently came from. It orbits close to Proteus, the large inner moon. And the thinking, the model that makes most sense of the numbers and the positions, is that Hippocamp is a fragment of Proteus, a piece that was knocked loose by an ancient comet impact, a chip that separated from its parent moon and, rather than drifting away or falling back, settled into its own nearby orbit and has been travelling there ever since. A moon that is, in a sense, a moonchild, born from another moon by the percussion of a collision. A small shard of a larger world that found its own path and held it. This, too, is a story of violence that became order, a collision that did not destroy but subdivided. A single large body that became a large body and a small companion, the companion inheriting a piece of the parent's mass and a piece of the neighbourhood space and going on from there. In the dark, in its own quiet loop around Neptune. The inner moon system of Neptune is, in this sense, a family of survivors and descendants, each of its members carrying in its composition and its orbit some trace of the history of disruption and reassembly that made this part of the solar system what it is. Naiad and Thalassa, with their locked dance born from rubble. Hippocamp, with its origin in collision. Proteus, its parent body, marked by the impact that took a piece of it and made something new. And behind all of it, Triton, still travelling backward, still announcing its foreign birth, the original disruption whose arrival set all the rest of this in motion. There is one more piece of the neighbourhood worth knowing as you rest with all of this, and that is the rings. Neptune has rings. Not the grand, sweeping, unmistakable rings of Saturn, which you can see in a modest telescope from Earth, but rings nonetheless, faint, dark, narrow, dusty structures that orbit the planet at various distances and were definitively confirmed by Voyager 2 in 1989 during that same brief, unrepeated visit that first showed us Naiad and Thalassa. Among these rings is one called the Adams Ring, and the Adams Ring has a feature that planetary scientists still find beautiful and slightly puzzling. It contains clumps of denser material called arcs, localized concentrations that are distributed unevenly around the ring rather than spread smoothly. A ring that is not quite continuous. A ring that has gathered itself into particular places and thickened there as if it were reluctant to spread fully out. And keeping the Adams Ring and its arcs in something like their current configuration is a moon called Galatea, one of the inner sibling moons of Naiad and Thalassa, whose gravitational influence acts as a shepherd. Galatea tends the ring. It nudges the ring material into and back from particular regions of space, maintaining the distribution of the arcs through a relationship of orbital influence that is itself another form of gravitational choreography. Another example of moons and material finding a stable configuration that they then maintain not by force but by the continuous. Patient application of their positions and their masses. Naiad and Thalassa live inside all of this. Their orbits are embedded in this dusty, ringed, multi-mooned environment. They thread their repeating over and under path within a system that is itself a web of gravitational relationships, each moon influencing and being influenced by its neighbours, each part of an arrangement that has taken a very long time to become as stable as it currently is. When Naiad rises over the top of Thalassa's orbital plane and then sinks beneath it, it does this inside a place that is streaked with faint rings and watched over by sibling moons, in a deep cold dark lit by a sun that is so far away it gives less than 1/900th the light that falls on any field or street or rooftop where you are lying now. And the question that sometimes arises when you look at a system like this, when you see how the pieces have settled and how the orbits are maintained, is a gentle one. How long will it last? The answer, for the purposes of anyone alive today, or anyone likely to be alive for a very long time, is longer than you need to think about. There are models, careful mathematical models, of the kind that planetary scientists construct to think about the long-term evolution of orbital systems that suggest Naiad orbiting as close as it does to Neptune inside what is called the synchronous orbit distance, the distance at which a moon's orbital period would match the planet's rotation, is subject over enormously long timescales to a process called tidal decay. Tides are not just the rising and falling of ocean water, they are a gravitational phenomenon, a flexing and deforming of bodies caused by the difference in gravitational pull across the width of an object, and they carry energy. When a moon orbits close to a planet, the tides that the moon raises on the planet and the tides that the planet raises on the moon drain a tiny fraction of orbital energy away in each circuit, so slowly and so incrementally that the change in any single orbit is immeasurably small but real and cumulative over time. For a moon inside the synchronous distance, the net effect is that the orbit slowly, imperceptibly shrinks, so slowly that the word slowly is not quite adequate, so slowly that tens of millions of years might pass before the change becomes substantial. What happens at the end of that process, in the models, is that the moon either falls inward toward the planet and is broken apart by tidal forces into a ring, or falls inward and is absorbed. The dance does not continue forever, if forever means to the heat death of the universe. But this is not a reason to feel anything other than at ease, because the scale of time involved is so vast, so incomprehensibly extended beyond anything that has meaning in a human life or a human civilization or a human species, that it has no practical relationship to tonight, or to any night you will ever see. For as long as anyone will ever stand anywhere and look up and think about the moons of Neptune, the dance holds. For as long as any instrument built by human hands will be able to observe the inner system of Neptune, Naiad will be rising over the top of Thalassa's orbit and sinking beneath it on its locked 73 to 69 count. The same clean miss that has repeated since before those moons were found, since before there were people to find them, since long before the ship that first showed them to us had even been conceived of or built or launched into the dark. And that ship. Voyager 2 launched in the summer of 1977. Not the summer that the resonance was decoded, not the summer that Naiad was refound in Hubble images, but 12 years and more before any of that, in a summer when the distance between Neptune and a human-made spacecraft was still a theoretical thing, a planned thing, a hoped-for thing that required a particular alignment of the outer planets that would not come again for a very long time. The people who designed Voyager 2 knew they had one window, one angle of approach, one opportunity offered by the geometry of the solar system to send a spacecraft past Jupiter and Saturn and Uranus and Neptune in a single continuous journey. They used it. They launched into it. And then they waited. 12 years. Jupiter in 1979, Saturn in 1981, Uranus in 1986. And then Neptune at last on August 25, 1989, a Tuesday in late summer, with Voyager 2 making its closest pass roughly 4,950 kilometers above Neptune's north pole, moving too fast to stop, too committed to its trajectory to do anything but pass through and keep going. carrying its cameras and its instruments into and out of the Neptune system in a window of close observation that lasted hours, not years, hours in which it found Naiad and Thalassa and Proteus and Despina and Larissa and confirmed the faint rings and sent all of that data back across 4.5 billion kilometers to people sitting in rooms in California waiting for the light speed signal. That would take hours to arrive. After Neptune, Voyager 2 did not stop. It had no reason to stop and no mechanism to stop, even if it had wanted to. It continued outward, past the orbit of Pluto, past the boundary where the sun's solar wind meets the thin material of interstellar space, and it is still going. As of the most recent information, decades after its Neptune flyby, Voyager 2 is still operating, still transmitting, still in contact with the people on Earth who built it, still sending data back from a distance that makes the word distance feel insufficient. It is, in some deep and simple sense, the farthest thing that human hands have ever made and sent away. One of two human-built objects, the other being its sibling, Voyager 1, that have crossed into the space between stars. It saw Naiad and Thalassa for a few hours, in passing, and it never came back. No spacecraft has come back. The moons have had no further visitors from the third planet of the inner solar system. They have gone on doing what they do, in the dark, with the same precision and the same unhurried reliability, observed only from a distance by a telescope in Earth's orbit that has had to wait for specific windows of visibility, has had to accumulate observations over years of careful tracking, has had to do the slow and patient mathematical work of finding the orbit inside the data. But even from that distance, even with that patience, what emerged was enough. Enough to reconstruct the tilted track, enough to identify the 73 to 69 lock, enough to know that Naiad was lost and then found again, that the dance had been happening the whole time, that the moons had not needed anyone to watch them in order to keep the weaving going. They kept it going in the dark of a system 30 astronomical units from the sun, in a cold so deep that any analogy breaks down before it arrives, in an environment of faint rings and dusty arcs and captured intruder moons orbiting backward, keeping their rhythm with the same indifference to observation that all natural processes have, ticking through their counts whether or not any instrument was pointed at them. And that indifference is not coldness. It is something closer to the opposite of coldness. It is the dependability of a thing that does not need to be watched in order to work, a thing whose mechanism is built into it so thoroughly that it requires no maintenance, no oversight, no corrective intervention, a thing that simply continues. There is a thought that sometimes visits people in the late hours, when the mind is tired but not quite resting, when the ceiling is close and the worry has been running quietly for a while without resolution, the thought that something is about to go wrong, that the gap between what is and what could be is too narrow, that the margin is too thin, that whatever has been holding things in their proper arrangement might at any moment fail, that the near miss is about to stop being a miss. Naiad and Thalassa have been having the same near miss for a time that makes the word ancient seem like an understatement. Their orbits are separated by less than 2,000 kilometers. They move fast enough that they circle their planet in about 7 hours. They catch up to each other repeatedly, lapping and being lapped, and every single time, every single pass in that enormous accumulated count, the tilt has been enough. The 73 to 69 timing has been exact. Naiad has risen over Thalassa's path and then dropped beneath it, or dropped beneath and risen over, and the separation at closest approach has held at something around 2,800 kilometers in the vertical direction. A distance that sounds thin until you remember that the mechanism guaranteeing it is not luck or hope or the continued patience of something that might lose interest, but the deep, structural, gravitational choreography of two objects that have found each other's rhythm and hold it in the way that all stable orbital systems hold what they have found, not by trying, but by being. The resonance is self-sustaining. That is what the modelling shows, and it is the part worth carrying to sleep. The mutual gravitational influence of the two moons does not erode the arrangement over time. It maintains it. Every pass, every close approach, the gravitational nudge that each moon gives the other acts not to disturb the dance, but to correct it, to reinforce the tilt and the timing, to keep the phase lock in place. The system repairs itself as it goes. It finds the same answer every time, not because it is trying to find the answer, but because the answer is built into the relationship between the masses and the distances and the speeds, and finding it is simply what happens when you let those quantities interact. The collision never comes, not because the moons are careful, but because the physics is arranged such that carefulness is not required. That is the thing to rest with, if anything tonight is worth resting with. Not just that the moons are safe, but why they are safe. Not just that the near miss resolves peacefully, but that the resolution is structural, mechanical, written into the orbit by the same gravity that shapes every large thing in this universe. That the peace is not fragile. That two small dark worlds in the outer dark around a cold blue planet have found their way to an arrangement where the danger, the genuine proximity, the real and measurable nearness of their orbital paths does not lead to collision, does not lead to catastrophe, does not lead anywhere but another safe pass, another clean separation. Another circuit completed in the right order and at the right time. They were made from rubble. They were assembled from the debris of a system that was broken apart by something enormous falling in from the dark. And out of that breaking, out of that slow reconstruction, came this exact dance, this tilted track, this integer lock, this perpetual near miss that always resolves. They were here before anyone knew about them. They were doing this before Voyager 2 made its 12-year journey and its few-hour pass and looked at them and sent their images home. They were doing this before Showalter's team sat with Hubble observations and did the careful mathematics and found the resonance and described it and published it and gave us a way to understand what had been happening in the dark all along. They were doing this before the name Naiad was given to the innermost of them, before anyone thought to name a small dark moon for a freshwater nymph or thought to call its neighbour for the primordial sea. They were doing this in a silence and a darkness and a patience that preceded all of that, and they will continue doing it long after any of tonight's concerns have dissolved into the ordinary passage of days. The sun rises at Neptune the way a distant, very bright star rises, not warming, not flooding the surface with heat and colour, but present, a point of light that is 900 times less bright than the sun you know from summer mornings, a star among stars that happens to be slightly brighter than the rest. That happens to be the one whose gravitational pull keeps this whole enormous system of planet and moons and rings in its circuit through the outer dark. The light that falls on Naiad and Thalassa as they thread past each other is about as much light as falls on the floor of a dimly lit room. And in that twilight, in that cold, in that distance, The dance continues with an exactness that no human activity has ever matched for duration. The same step performed the same way for longer than there have been mountains on Earth. If you are somewhere in the world tonight, lying still, listening to this, and somewhere you are, because here you are, then you are lying on a planet that is, in the accounting of the solar system, a warm and busy and intricately complicated place. A planet covered in water and air, and a thin shell of life going about all the urgent and frightened and hopeful business of living. A planet that is, itself, doing its own kind of orbital dance around its own star, maintaining its own tilted, almost circular path, influenced by its own gravitational relationships with the other planets around it. Never quite perfectly stable, but never catastrophically disrupted either, finding its balance in a solar system that is, for now, for this era, for this vast and unhurried segment of time, arranged in something close to order. You are part of a system that has found its stability the same way Naiad and Thalassa found theirs, not by avoiding disruption. Not by keeping everything perfectly still and perfectly simple, but by finding, through the long process of settling and interaction and adjustment, the arrangement that holds. That continues. That resolves the near miss and makes another circuit and comes around again. The dance is still going, right now, as you lie still, 4.5 billion kilometers from where you are, in a darkness that makes night here seem like afternoon. Two small, dark, potato-shaped worlds are doing what they have always done. One rising over the other, then sinking beneath it, held apart by a tilt of about 4¾ degrees and a count of 73 laps to 69. Maintained by the quiet authority of their mutual gravity in a system born from catastrophe and settled into peace. They are not waiting for permission to continue. They are not watching to see if anyone is still paying attention. They are simply doing what the physics says they will do, in the cold, in the dark, in the deep patient arithmetic of a universe that has no particular interest in being dramatic about it. If you feel moved to tell me where in the world you are listening from tonight, what corner of this warm, complicated, orbiting planet you have settled into for the hours of dark, I would genuinely like to know. The comments are there, and I read them. And there are more stories here of this slow kind, waiting for whenever you want them, whenever the night feels long, and something quiet and real and carefully told would help you find your way to rest. But for now, the passages are quiet. The orbits continue. Naiad is somewhere in its arc right now, on its way toward the pass, climbing the gentle incline of its tilted track, preparing in the way that things with no awareness prepare, which is to say, simply proceeding, simply being in the place the physics puts it, at the time the physics puts it there, on its way to another clean miss that it will complete with the same indifference to outcome it has always had. And Thalassa is there ahead of it or behind it, nearly flat in its plane, going around and around in its 7-hour loop, waiting in the way that things with no awareness wait, which is to say, simply continuing, simply occupying its orbit as it has always occupied it, in the dark, in the near dark, in the 1/900th of noon that passes for daylight out there at 30 astronomical units from the nearest warmth. They were made from the remnants of something broken. They found their rhythm. They have been keeping it ever since. You can let go of watching it. It does not need you to watch it. It will keep going. Good night from up here in orbit. I'll keep watch while you drift.